Welcome to the Solutions Part 4 Screencast for Chem 1B at Shasta College. This will be the final screencast for the Solutions unit. In it we'll do a couple problems that were skipped over during this week's classes, and then there's a little bit of additional material that will be covered as well. Let's start with question 11, which is one of the questions that was skipped over during this week's class. It deals with the drug cocaine, and the presence of cocaine in a person can be determined by testing their urine, and mass spectroscopy is able to detect cocaine in urine at a concentration as low as 150 nanograms per milliliter. So the question is, what is this concentration as a molality? So to solve this problem, we have to recall that molality is moles of solute, and our solute is cocaine, per kilogram of solvent, and our solvent is urine. So we'll use blue for cocaine and red for urine and go through our conversion. And note that what we have a 150 nanogram per milliliter solution, so why don't we just assume we have 1 milliliter of solution? It contains 150 nanograms of cocaine, and we want to turn that into moles of cocaine, so we can convert nanograms into grams by noting that a nanogram is 10 to the minus 9 grams. And then we have 303.4 grams. That's equal to 1 mole of cocaine. And when we calculate this, what we find is it's equal to 4.944 times 10 to the minus 10th moles of cocaine. And we're carrying an extra sig figure too here. Now, we also have to do our conversion from milliliters of urine into kilograms of urine. So there are 1.025 grams per milliliter for urine. We're given the density in the problem up here. And then, of course, there's 1,000 grams per kilogram. And if we do that calculation, then we have 1.025 times 10 to the minus third kilograms of our solvent urine. And now, of course, the original ratio was 150 nanograms of cocaine per milligram of urine. If we do the conversions, then we can take this ratio. And so what we will have here is, when we divide this out, we get 4.823 times 10 to the minus 7th moles per kilogram. And this is too many sig figs. Probably the 150 nanograms here very likely is only good to 2 sig figs. I'm going to assume here that the 0 isn't a sig fig, and if that's the case, we should round this off to 4.8 times 10 to the minus 7th moles of cocaine per kilogram of solvent, kilogram of urine, and we can symbolize that by lowercase m. So there is our answer. Now, the second question that we skipped during last week's classes was number 14, which deals with a 1 molar solution of sulfurous acid, H2SO3. It's found to freeze at negative 2.01 degrees Celsius. And the question is, what's the Van 't Hoff factor for this solution, and what does this mean? Now, note that in previous problems of this type, we've typically looked at the solutes formula, and from that deduced the Van 't Hoff factor. We've figured out how many pieces it dissociates into. But in this case, we have sulfurous acid, which is a weak acid, Weak acids only partially dissociate into their constituent ions, and so we're going to actually, from figuring out the Van't Hoff factor, be able to tell something about the extent of this dissociation. So to do this, we note, of course, that we have a freezing point depression problem, and the freezing point depression is equal to the freezing constant times the molality times the Van't Hoff factor, and the molality can also be written as moles of solute per kilogram of solvent, and we can then solve this problem or this equation for I by rearranging appropriately. And if we do that, what we end up getting is I is equal to the temperature difference, how much the freezing point goes down, times the kilograms of solvent, and divided by the freezing constant as well as the number of moles of solute. So the delta T freezing, water freezes at 0 degrees Celsius, the solution freezes at negative 2.01 degrees Celsius, so the freezing point depression is 2.01 degrees Celsius. The freezing point constant is a lookupable number, 1.86 degrees Celsius kilogram per mole. And then the moles of solute and the kilogram of solvent can be determined from the concentration of the H2SO3, but unless we know its density, we're going to have to do some estimating. And so what we do is we'd say, well, let's assume that we have a 1 liter of solution, so we have 1 mole of solute, and we have that in 1 liter of solution. And now this solution is going to have a density that's higher than 1 gram per milliliter, and it's probably going to be maybe 1.05 to 1.1 grams per milliliter or so, based upon values of other substances or other solutions we've seen like this. And so a decent estimation might be to say, well, if we have 1 mole of H2SO3, that's about 82 grams of H2SO3, and then 1 liter of solution, if that was made by taking 1,000 grams of water and adding that to a 1 mole or 82 grams of H2SO3, that would give us 1,082 grams of solution. And if that 1,082 grams was in, or the volume of that was 1 liter or 1,000 milliliters, then that would be a density of, so it's 1,000 milliliters. That would be a density of about 1.08 grams per milliliter, which seems like a pretty reasonable density for H2SO3. So let's use that as our approximation. We'll say that we have approximately 1 mole. Well, we have 1 mole by choice, and that corresponds to approximately 1,000 grams. Remember, it's of our solvent. So we have about 1,000 grams or about 1 kilogram of our solvent. And what this means is that I, when we do the math, degrees Celsius cancel, moles cancel, kilograms cancel, and I works out to be about 1.06. And now note what that's going to mean is that the H2SO3, which dissociates primarily into H plus and HSO3 minus, and as we'll see later, it turns out the HSO3 can further dissociate into H plus and SO3 2 minus. Well, that only dissociates nothing like to I equals 2, and what this would mean is it only dissociates about 6%. So if we had, let's say, 100 H2SO3 molecules, then it would, about 6 of them would dissociate, and that would form 6 H pluses and 6 HSO3 minuses. and that would leave about 94 H2SO3s that didn't dissociate. So this is a measure of percent dissociation, and this is something that we will deal with in future chapters a fair amount. Now, we just saw that the Van Hoff factor for something like a weak acid can't be predicted just by looking at the formula of the compound. And it's also worth noting that even for compounds that we've been predicting Van Hoff factors for, that's an idealized version, which is true in a lot of cases, but it does change for some substances as their concentration changes. So, for example, sucrose, a molecular compound, we've said has an I of 1 because it doesn't break apart into particles. And that's pretty much true. As the solution concentration goes from pretty dilute to less dilute or more concentrated, the Van Hoff factor for sucrose pretty much just stays 1. But for sodium chloride, which we've been saying has an I of 2, well, that's ideally it's 2, and it's true for very dilute solutions. But as the solution concentration goes up, the Van Hoff factor deviates more and more from its ideal. It gets less and less close to 2, and in fact it becomes a smaller number. This is because as the solution gets more concentrated, there's more solute particles in the solution, and at any given instant it's more likely that a couple of those solute particles are stuck together or so close together that they basically behave as one particle, and that effectively reduces the concentration of individual particles. And this gets more and more the case as the solution gets more and more concentrated. And here's one more example now for potassium sulfate. Ideally 3 particles, but as the solution concentration goes up, the Van Hoff factor actually decreases somewhat significantly for the reason just discussed. Now, aside from the outstanding mullet in this picture, this is an example that's worth noting called dialysis. And when people have poorly functioning kidneys that don't clear the waste products out of their bloodstream properly, then they may have to go on dialysis to clean the blood and allow them to continue to have kind of a decent life. The reason this is being mentioned is because this is another example of osmosis, but in a different way than we've seen. So this is kind of a little cartoon schematic of impure blood going through the dialysis machine, and it is pushed through or flows through a dialyzing solution, and there's a semi-permeable membrane that surrounds the blood, separates it from the dialyzing solution. And remember that semi-permeable membranes allow some substances to pass through and not others. Normally, it's small molecules like water that pass through, and proteins and other things aren't able to get through. But the membrane that's used for dialysis is a special membrane that actually allows the waste products like urea and things like that to pass through it. And so what ends up happening is waste products, let's say urea, is passing through, is dissolved in the blood, and as it passes through the dialyzing solution, since urea can get through this, then there's a high concentration of urea in the impure blood. There's initially no urea in the dialyzing solution around it, and so what's going to happen is as the blood flows through, the impure blood flows through, some of the waste products are going to pass through the semi-permeable membrane into the dialyzing solution, thus cleaning the blood, and basically it just goes through enough dialyzing solution to get it pretty darn clean. Now, one other example of osmosis is how we get more drinkable water, and in some places in the world there's very little of that, especially places in the Middle East or for that matter California in the South. And how we can get more potable water, it's been literally suggested that we send ships to tow icebergs from, let's say, the Antarctic to places that need fresh water. Now, that's at least theoretically doable. You can get an iceberg there without it all melting. But maybe a better idea is to use a process called reverse osmosis, which is the opposite of what we normally have happen in osmosis. So normally, we've seen this before, we have a pure solvent on the left side of this U-tube, semi-permeable membrane, on the right side a solution, and let's say that it's salt water, and in order to make this salt water pure, or at least to extract pure water from it, what we can do is note that normally the solvent, the water molecules, would tend to flow this way, and it would make this side of the U-tube have a higher solution, go up higher in the tube. This would decrease. But if we add pressure on this side, if we add enough pressure, we can force the water molecules to go through from the saltwater solution in and into the other side of the U-tube. And so this is a way to purify water. It ends up concentrating the saltwater solution. And so there's a couple big problems here. One is the pressure's high enough that it's tough on the membrane, and so the membrane has to withstand a pretty high pressure but still be porous enough to let water go through. And then the other thing is, actually two more things. We have some waste salt that we have to get rid of, but that's often not too big of a deal. And then it costs a certain amount of energy, fair amount of energy, to create this pressure. And so we can get net solvent flow to go in the opposite way by a process called reverse osmosis, and that's used to purify water in quite a few places in the world. There's a couple plants in Southern California, and a place like Israel gets a tremendous amount of its water from purifying salt water via reverse osmosis. One more thing along the lines of an example of solubility is, if you've ever wondered how soap works, this is an example of a soap molecule, and notice there's a lot of non-polar part of it here, and then there's a polar end or tail to the molecule. And soap molecules are made this way because the non-polar part does a good job of dissolving in grease and oil. The polar part does a good job of dissolving in water. And so if you add soap to your dirty clothes or dishes and have a bunch of water, then the grease or oil can dissolve in the non-polar end, the water can be attracted to the polar end, and then the water kind of, as it flows by, pulls the grease away, and these things tend to form what are called micelles, where here's a little tiny oil drop, the non-polar ends of a whole bunch of water molecules dissolve in it, and then on the surface of the drop are a bunch of these negatively charged tails of the soap molecules. They're attracted by water, which carries this away, thus cleaning. And the last thing to consider is just to look at the solution process in terms of enthalpy or energy of the process just a little bit. And early in the unit, we talked about how a solution forms, and one way to think about it is in terms of maybe three possible steps where you have some solute and the molecules or ions or whatever it is of the solute get separated. And then the solvent, same thing, you have some molecules and they get pulled apart. And then those things get mixed together and then they kind of come back together again. So we're imagining this is happening in three steps. It really doesn't happen in separate steps. It all kind of happens all at once. But to pull a solute or a solvent, a bunch of molecules apart, both of those are going to require energy. They'll be endothermic steps. But then putting them back together again, so we have a bunch of separated particles and then they then draw back together, they attract each other, and they give off some energy. That's an exothermic step. And note that we can add up these three equations, and we make solute apart, but then the solute apart contributes to make solution. We make solvent apart, but then it cancels out with solvent apart to make solution. And if we add these three equations together, then we get solute plus solvent makes solution. And now that is going to be possibly positive and endothermic or possibly negative and exothermic, depending upon how big these values are relative to each other, because you have some positive values and some negative values, and when you add them up, whether the total is positive or negative depends upon their relative magnitudes. And here's a way to look at it kind of in a graphical manner. We have solute and solvent. Some energy is needed to pull the solvent-solvent particles apart. Some energy is needed to pull the solute-solute particles apart. And then energy is given off when the solvent and solute particles get together. And if the energy total needed to pull the solute and solvent apart is less, and the energy given off when the solute-solvent forms is more, then overall we have a delta H for the solution that's negative. Now, and of course that's an exothermic process. Now we could just as easily have the solvent-solvent and solute-solute interactions, which both are positive, add up to something that's less than the solvent-solute amount of energy given off, and then we would have an overall delta H for the solution process that's positive, and that would be endothermic. And typically these two and compared to that one, so these two compared to that one, usually the balance is pretty close, and so what ends up happening is the delta H for solution for ionic compounds, which is what we're looking at here as examples, notice they're not that big numbers. Some are negative, some are positive, and for our purposes, just sort of to realize that the balance is close. Sometimes it ends up overall being positive, sometimes it ends up overall being negative, is probably sufficient. So that is it for solutions. End of part 4 screencast.